As physicists, we've enthusiastically guessed this for over a century, starting in the year 1916. This event marks a momentous accomplishment, offering a brief look into one of the universe's most captivating and cryptic peculiarities: dark holes. These grandiose monsters, known for their enormous influence, remain extraordinarily elusive. While they are epic in terms of their gravitational impact, they are nearly undetectable, making them even more puzzling. One such dark hole, possibly weighing between 2 to 4 million times the mass of our Sun, may be the subject of this discovery. Over the past several decades, research devoted to dark holes has transformed our understanding, taking us from a place of absolute ignorance to one where we are beginning to get a close look at them. And now, things have taken an even more thrilling turn, as physicist Michio Kaku has revealed that we have finally figured out how to look inside a dark hole. This discovery opens the door to a wealth of new information that could illuminate aspects of science we may have overlooked in the past. Let's take a deep dive into the realm of dark holes and uncover what exists within them. While space is limitless and vast, the concept of dark holes raises endless inquiries. The history of dark hole research. Before we begin discussing the specifics of Kaku's remarkable findings, it's essential to understand the basic nature of dark holes. While there is widespread acceptance of what dark holes are, significant gaps in our knowledge remain. The theory of dark holes dates back to 1916, when Albert Einstein published his general theory of relativity. This theory predicted the existence of dark holes. Despite the fact that, at the time, the idea was solely theoretical, it wasn't until about 50 years later, in the 1960s, that substantial evidence for their existence began to surface. Researchers studying the constellation Cygnus observed an unusually bright blue star emitting X-rays. They found that this star was not stationary, but rather orbiting a huge dark object. Upon further examination, it became clear that these X-rays were being incorporated into the object, leading to the coining of the term dark hole. This discovery was a historic turning point, proving that dark holes were not just a product of Einstein's imagination. They were real, tangible entities that existed in space. It became clear that we needed to study them in greater detail. Scientists from around the world began focusing their research on a specific dark hole in the Cygnus constellation, designated Cygnus X-1, which lies approximately 6,000 light-years from Earth. This dark hole was millions of times brighter than the Sun and exhibited extreme density, with a gravitational pull so intense that not even light could escape it. This was the primary characteristic of a dark hole: the ability to trap light within its gravitational embrace. Understanding the nature of dark holes. The nature of a dark hole is both fascinating and terrifying. A dark hole is a region in space where gravity is so strong that nothing, not even light, can escape it. Any object that ventures too close to a dark hole is sucked in, and once it passes a critical boundary, is lost forever. This inherent danger is why it is crucial to expand our understanding of dark holes. After the discovery of Cygnus X-1, researchers launched an extensive search for other dark holes. Current estimates suggest that there may be over 100 million dark holes scattered throughout the Milky Way galaxy. However, due to their nature, these cosmic giants are incredibly difficult to detect, meaning we do not have an exact count. One of the main concerns surrounding dark holes revolves around their gravity. Their gravitational force is so immense that anything getting too close is gradually compressed to an extreme degree until it becomes a dark singularity. To put it simply, dark holes function as cosmic vacuum cleaners, pulling everything in with an insatiable force. One of the most unsettling aspects of dark hole research is that if someone were to fall into one, they would be stretched into a long, thin shape due to the tidal forces acting upon them. This stretching would occur gradually, and the individual would perish before reaching the final stage of this process. So, to be clear, it's best to avoid falling into one at all costs. Although the nearest dark hole is about 500 light-years away, it still raises questions about the possible threats they pose to us. The first image of a dark hole. In 2021, a remarkable achievement was accomplished when scientists successfully captured the first clear image of a dark hole. This particular dark hole was located in the galaxy M87. The research team took a number of pictures over several nights, and by stitching these images together, they created a comprehensive photograph that revealed stunning details. It appears that a dark hole is not just a giant void of nothingness, as many people assume. In fact, a dark hole consists of three distinct layers. 1. The event horizon. Once an object crosses this boundary, there is no turning back. It will inevitably be pulled into the dark hole. 2. The photon sphere, a region where light itself can be trapped in orbit around the dark hole. Any light entering this area becomes trapped by the dark hole's gravitational force, unable to escape. 3. The singularity, the point at which everything that falls into the dark hole is crushed down to an infinitely small point. This is where the laws of physics, as we know them, completely break down, making it impossible to predict what happens next. Theoretical possibilities, wormholes, and time travel. What's even more intriguing and alarming is that no two dark holes are exactly alike. While they all follow this three-layer structure, their behavior can vary significantly. One theory suggests that dark holes may be connected to wormholes, hypothetical passageways that link two separate regions of space-time. Some theories even suggest that they could link parallel universes. If someone were to fall into a dark hole, rather than being crushed, they might travel through this wormhole and emerge in a different universe, or even at a different point in time. According to Einstein's theory of relativity, space and time are intertwined, forming a four-dimensional fabric. Objects with mass distort this fabric, creating a gravitational field that causes other objects to move toward them. Imagine space-time as a sheet of paper. If you place 2 points on it and draw a boundary between them, that represents the path objects take through space-time. However, if you could fold the paper, you would create a shortcut between the 2 points, much like a wormhole connecting two distant regions of space-time. The future of dark hole research. Wormholes are not just science fiction. They're a direct prediction of general relativity. However, no one has observed one yet. Intrinsically temperamental, wormholes can implode very quickly. The potential for wormholes to act as movement pathways through existence has fascinated physicists for a long time. While the idea of traveling vast distances in a moment, or even venturing through time, is unquestionably thrilling, Einstein's special theory of relativity predicts that nothing can travel faster than the speed of light, which places an absolute restriction on wormhole plausibility, at least with our current understanding of physics. Physicist Michio Kaku has been working on a unified theory that might help explain dark holes. One of the greatest challenges in modern physics is reconciling general relativity with quantum mechanics, two powerful yet seemingly incompatible frameworks that describe the universe at vastly different scales. While Einstein's theory of general relativity explains gravity and large-scale cosmic structures, quantum mechanics governs the behavior of subatomic particles. Dark holes exist at the intersection of these two realms. They are massive cosmic objects, yet they also contain singularities, infinitely small points where space and time break down. To truly understand dark holes, scientists must develop a unified theory that merges these two pillars of physics. Physicist Stephen Hawking made significant contributions to this pursuit with his theory of Hawking radiation. In 1974, he proposed that dark holes are not completely black, but instead emit tiny amounts of radiation due to quantum effects near the event horizon. Over time, this radiation causes the dark hole to lose mass and eventually evaporate, a process that challenges the long-held belief that dark holes are eternal. Hawking radiation introduces a paradox. If a dark hole eventually evaporates, what happens to the information about everything that fell into it? This information paradox remains one of the greatest unsolved mysteries in physics. According to quantum mechanics, information cannot be destroyed, but if a dark hole vanishes, it seemingly takes all its information with it. Could dark holes be gateways to other universes? Theoretical physicists have long speculated that dark holes could serve as gateways to other parts of the universe, or even to entirely different universes. This idea is based on the concept of Einstein-Rosen bridges, commonly known as wormholes. If wormholes exist, they could provide shortcuts through space-time, allowing for faster-than-light travel. However, they remain purely theoretical, and their stability is uncertain. Many physicists believe that exotic matter, material with negative energy, would be required to keep a wormhole open long enough for anything to pass through it. One intriguing idea is that what we perceive as a dark hole could actually be a white hole in another universe. Unlike dark holes, which trap everything that enters, white holes are hypothetical objects that expel everything, making them the opposite of dark holes. Some theories suggest that every dark hole could lead to a white hole in another part of the cosmos, creating a cosmic tunnel between universes. While these ideas remain speculative, they inspire new research into the true nature of space-time and the fundamental laws governing our universe. The future of dark hole exploration. As technology advances, scientists are finding new ways to study dark holes. The Event Horizon Telescope, EHD, which captured the first image of a dark hole in 2019, continues to refine its observations, revealing new details about these enigmatic objects. Future missions, such as the Laser Interferometer Space Antenna, LISA, aim to detect gravitational waves, ripples in space-time caused by dark holes merging. By studying these waves, scientists hope to gain insights into the formation, evolution, and behavior of dark holes across the universe. Additionally, proposals for quantum gravity theories, such as loop quantum gravity and string theory, may provide new ways to understand dark holes at the quantum level. These theories suggest that the singularity at the heart of a dark hole might not be an infinitely small point, but instead a complex quantum structure that obeys yet undiscovered laws of physics. Final thoughts. The endless mystery of dark holes. Despite all the progress made in dark hole research, many questions remain unanswered. What truly lies beyond the event horizon? Is information really lost in a dark hole, or can it be recovered? Could dark holes serve as portals to other universes, or are they merely cosmic dead ends? As physicists like Michio Kaku and others continue pushing the boundaries of knowledge, we inch closer to unlocking the secrets of these cosmic giants. Whether through quantum physics, advanced telescopes, or space-based observatories, the next few decades may bring revolutionary discoveries that reshape our understanding of space, time, and reality itself. For now, dark holes remain one of the most awe-inspiring and mysterious phenomena in the universe, reminding us that, despite all our knowledge, the cosmos still holds countless secrets waiting to be uncovered. Research into black holes is filled with speculation and exploration. Beyond their obvious role in shaping space-time, black holes have become central to discussions about the origins of the universe itself. String theory suggests that cosmic collisions could lead to the creation of new universes, and black holes could play a significant part in this process. According to one theory, our universe may have been born from the collision of two previously existing universes. Or perhaps, if we are within a black hole, this idea, if proven correct, could challenge everything we assume about the Big Bang. We might begin to see black holes not just as destructive forces, but as potentially creative ones, gateways to other realms or parallel universes. While the notion that black holes could function as portals to other universes or provide the potential for time travel is intriguing, it remains within the realm of theoretical speculation. The mechanics of wormholes and the ability to navigate through them remain significant mysteries. Even if wormholes were stable, the extreme radiation and forces near these structures would likely make them impassable. Some physicists speculate that if we could stabilize a wormhole, it could theoretically allow travel through time or between distant points in the universe. However, this remains a distant dream given our current technology and understanding. When we examine black holes through the lens of quantum mechanics, we encounter even more perplexing questions. The behavior of particles at the quantum level is fundamentally different from what we experience at macroscopic scales. The laws of physics appear to break down completely when we consider objects like black holes. This difference between quantum mechanics and general relativity has been one of the most difficult obstacles in theoretical physics. Theorems in theoretical physics, such as superstring theory, offer a possible framework for reconciling these distinctions by introducing additional dimensions and offering fresh perspectives on the nature of gravity. Despite this, the theory has yet to be experimentally confirmed, and many of its predictions remain untested. Theoretical physicists like Michio Kaku are working tirelessly to unify these two major pillars of physics, quantum mechanics and general relativity, into a single, unified theory that can explain the full spectrum of phenomena. A theory of everything at all scales would not only offer a deeper understanding of black holes and other exotic objects in the universe, but could also shed light on the very nature of space-time itself. The concept of extra dimensions, as predicted by string theory, may help explain the hidden forces that govern the universe. It suggests that what we perceive as 4 dimensions may actually be a small slice of a much larger and more complex structure. Another area of intense study is the role black holes play in the evolution of galaxies and the structure of the universe. The discovery that extremely massive black holes can be found at the centers of most galaxies, including our own Milky Way, raises further questions about their influence on star formation rates and galaxy evolution. Even the ultimate fate of the universe itself. The idea that black holes could play such a fundamental role in shaping the universe adds another layer of complexity to their already mysterious nature. Moreover, the intense radiation emitted by black holes, known as Hawking radiation, named after the renowned physicist Stephen Hawking, has led to fascinating discussions about the ultimate fate of information within a black hole. Scientists have debated whether information is lost forever when it crosses the event horizon of a black hole, a concept referred to as the information paradox. Hawking's groundbreaking work suggested that black holes could emit radiation that gradually causes them to evaporate over time, potentially resolving the paradox. However, this remains an active area of research with no definitive answers yet. What is clear is that the study of black holes has provided profound insights into the nature of gravity, space-time, and the universe as a whole. It has also opened the door to a new frontier in physics. Black holes challenge our comprehension of the laws of nature and continue to provide a foundation for novel theories and discoveries. As our observational tools improve and we explore deeper into the quantum and relativistic realms, we are likely to uncover even more profound truths about these enigmatic cosmic objects. The journey of exploration, like the mysteries of the universe itself, is bound to take us to places we never imagined. As we push the boundaries of our understanding, new questions arise. If black holes can act as cosmic engines shaping galaxies, could they also influence the fundamental nature of time itself? Some physicists propose that black holes might store information about the past, effectively preserving a record of the history of the universe within their event horizons. This idea connects to the ongoing debate about the information paradox. If information is not lost, where does it go in a black hole? One hypothesis suggests that the data could be encoded on the event horizon itself, an idea known as the holographic principle. This theory, developed by physicists like Gerard T. Hooft and Leonard Susskind, proposes that all the information contained in a 3-dimensional region of space could be stored on a 2-dimensional surface. If true, it would mean that our entire universe might function like a giant hologram, with our perception of reality being a representation of the underlying quantum information. Furthermore, if wormholes can exist as stable structures, they might be more than just cosmic shortcuts. They could also serve as information channels. Some researchers speculate that quantum entanglement, a phenomenon where 2 particles remain connected across vast distances, could be linked to microscopic wormholes, forming what is sometimes called the ER equals EPR conjecture, named after Einstein-Rosen bridges and the Einstein-Podolsky-Rosen paradox. If this conjecture holds, it could suggest a deep connection between space-time geometry and quantum mechanics, potentially leading to breakthroughs in understanding gravity at the smallest scales. The future of black hole research is promising. With advancements in observational technology, such as next-generation space telescopes and gravitational wave detectors, scientists hope to gain even more insights into black holes. The James Webb Space Telescope, JWST, has already begun providing unprecedented views of the early universe, while the Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will detect low-frequency gravitational waves produced when two black holes merge. These tools will help answer some of the most pressing questions in astrophysics, including how black holes evolve over time and whether they truly act as bridges between different regions of space-time. Meanwhile, laboratory experiments in quantum mechanics are shedding light on the mysteries of gravity. Some physicists are exploring the possibility of creating artificial black hole analogs using Bose-Einstein condensates, ultra-cold atoms that mimic certain aspects of event horizons. These experimental setups could help test some predictions of quantum gravity in a controlled environment. Could black holes be the key to a new understanding of the universe? As research continues, some scientists are beginning to entertain even more